Hi everyone, I'm Shen Huang and currently a PhD student at the University of New South Wales, Sydney, Australia. I'm very honored to be here to share our recent published work, all 3D printed antennas based on phase velocity control for beam steering and size reduction with low cost. In this work, we demonstrate a concept based on engineering a dielectric fielding material to adjust the phase velocity of the propagating electromagnetic wave in a horn antenna. Figure 1 shows the overall antenna design and details. We firstly designed the field dielectric air combined unit in the horn, providing a uniform phase distribution at the aperture to achieve a narrow beam. To realize the modification of the effective permittivity, the dielectric insertions are designed. These insertions follow the same shape of the air part of the unit. In Figure 1e, the thickness of the insertions increases from one side to another. Therefore, when the insertions advance through the air slot, the effective permittivity of the combined units is changed. The simulated field distribution are emphasized in this animation, where the first one shows that no insertions results in a radiation in the forward direction. The second one shows the field distribution in the horn is divided to the positive y-axis when only top-side dielectric insertions are rotated. The last one shows the radiation is steered to the negative y-axis when bottom-side dielectric insertions are rotated. Figure 2 shows a simulated E-plane pattern of these states. The maximum steering angle at 21 degrees is observed when the units are fully filled. The liquid crystal display 3D printing is used to fabricate the antennas. The surface of the horn and the waveguide are metallized by the conductive silver spray. For a more accurate measurement of the antenna, we measured the dielectric properties of the resin, including the relative permittivity around 2.75 and the loss tangent around 0.025 at 24 GHz. We show one side of the measured results. At 6 days of the rotation angle, it can be seen that the maximum steering angle around 20 degrees is obtained. And thank you very much for watching our video, and please feel free to contact us if you have further questions. Thank you.
Thanks for the invitation for making a presentation in Antenna and Propagation Society. I'm the president Zhang Yujie. Our research group is from the ECE department of the Hong Kong University of Science and Technology under the supervision of Professor Rose March. Today, I'm going to talk about the low-profile microstrip vertically polarized end-fire antenna with 360-degree beam scanning and high beam shaving capability. The traditional method to achieve beam scanning is to employ mechanically beam scanning reflectors. However, they are bulky, heavy, with slow scanning speed and without multi-beam scan capability. An improved and alternative technique is to employ electrically beam scanning phase arrays, but the main disadvantages: high complexity, high power consumption, and high cost due to a large number of RF phase shifters and TR modules required. For civilian applications, it's critical to develop low-cost beam scanning antennas. The pattern reconfigurable single-feed antenna can conduct beam steering without using any phase shifters, which is assumed to be one of the most promising ways for making compact size, low-cost wide-angle scanning antenna. However, previous pattern reconfigurable antenna design can only generate few radiation patterns, thus making a single-feed antenna highly pattern reconfigurable is the main research gap that we are focusing in this paper. We propose a planar vertically polarized highly pattern reconfigurable antenna by combining a low-profile electric dipole source with surrounded reconfigurable magnetite resonators. The center source antenna is obtained by shorting the edge of a circular patch to get a uniform magnetic current distribution. Thus, it can generate omnidirectional radiation pattern with vertically polarized electric fields. The height of this antenna is 4 times smaller than traditional monopoles. The surrounded elements are reconfigurable vertically polarized magnetite resonator within cell, which can reflect or transmit the coming waves by changing its working states. A certain antenna radiation pattern and the input impedance can be generated by optimizing the distribution of the working states of all the surrounded magnetite resonator, which is expressed as X here. As a result, this antenna can generate and fire single beam scanning among 360 degrees in the full azimuth plane with only 15-degree scanning resolution. Moreover, a flexible dual beam scanning with one beam pointing at 0 degree and the other beam scanning independently in the full azimuth plane is also achievable. Three beam pointing at three directions and even omnidirectional beam can also be found. These multi-beam radiation patterns are useful for precoding technology in wireless communication for multi-user scenarios. Here are some measured antenna radiation patterns that matches well with simulations. The antenna efficiency is around 80% for different radiation modes. In conclusion, I believe that the reconfigurable electromagnetic systems will promise significant performance gains in future wireless systems. Compared with conventional reconfigurable antennas with few states, this novel highly patterned reconfigurable antennas concept may be more interesting since it can control the EM waves more precisely. This highly patterned reconfigurable antenna may be useful for future low-cost small cell base station applications. Thank you for listening.
Hi, this video presents our work demonstrating a new beam steerable antenna for applications in 5G base stations. After severe congestions noted in the present sub-3 GHz band, millimeter wave bands are being extensively explored for 5G network. To deal with issues like atmospheric attenuation and path loss, beamforming and beam steering is considered as one of the key enablers for the technology, and hence here we focus on a leaky wave architecture based slot array antenna developed on a new corrugated SIW. Conventional SIWs have multiple wires running through the guiding structure, making it difficult to put active components, which are then replaced with inductive stubs in corrugated SIW. Here, these corrugations in a conventional CSIW are replaced with interdigitated capacitor. It presents a lower transmission loss of 0.7 dB compared to a conventional CSIW, which has a loss greater than 1.5 dB. Please note that the proposed IDC CSIW only works for TE10 mode, same as a conventional CSIW. The performance of such IDC CSIW is then verified using an equivalent circuit. A mathematical equation has been derived to calculate the cutoff frequency of such waveguide structures. It is derived using two components, that is, the cutoff frequency of an SIW of same width and the bandpass functionality that the IDC CSIW presents. The validity of the equation has been confirmed with parametric analysis. This IDC CSIW is used to create a 6-element slot array antenna. Pin diodes are placed within the corrugation, which allows the manipulation of surface current. The antenna is fed from both ends and is controlled using an SPDT switch. Here we can see the fabricated antenna with 30 pin diodes controlling the antenna. A set of 5 pin diodes are controlled simultaneously and is biased using the biasing line. The antenna was first measured with no biasings on the pin diodes. Here we can see the S11 for 2 feeds, and the antenna is working at 26 to 29 GHz band and has a very good match with simulated results. For each feed, the antenna has 2 beams pointing in 2 different directions because of the two different points of feeds. It has a total efficiency greater than 70% and a gain larger than 12 dpi. Pin diodes are used to control the beam direction. As shown earlier, a set of 5 pin diodes are controlled simultaneously, and here it is called a unit cell. This set of 5 pin diodes, when forward biased, it manipulates the surface current in a selective area and moves the signal towards the U-shaped slot created within the corrugations. This forward biasing allows for the change in beam direction and hence provides beam steering based on different corrugations of pin diodes. Here we can see a continuous beam steer between plus 60 degrees and minus 60 degrees in azimuth plane with an approximately stable gain of 13.5 dB. However, since the antenna is fed from 2 different sides, the beam gets split in 2 halves in the elevation plane, hence giving us a break in the continuous steering. This is resolved with 2-element array. 2 of such antennas are placed together as a mirror image and are fed from 4 corners using an SP4T switch. Here a 2.4 mm connector was used to feed the antenna, and male header pins were used to control the biasing paths for pin diodes and switches. The measured S parameters had a good agreement with simulation showing the same 26 to 29 GHz frequency band, and based on which feed point is used, the antenna provided a full 120-degree beam steer in azimuth plane and a 30-degree beam steer in the elevation plane. To summarize, we have presented an integrated digitated capacitor-based corrugated SIW, which is then used for a leaky wave architecture for a 6-element slot array, which is operating at 26 to 29 GHz frequency band and has a beam steering range of 120 degrees in azimuth plane and 30 degrees in elevation plane. The size of the antenna is very small, which is 75 by 22.4 mm, and it has side lobe levels greater than 15 dB. Thank you.